Hello. I am pleased to welcome you to the 16th annual Exploring Your Universe event. I am Miguel Garcia Garibay, Dean of the Division of Physical Sciences. With over 10,000 community members attending UCLA for Exploring Your Universe last year, this event has grown into the largest public science outreach event on campus, educating and engaging tens of thousands of visitors since its inaugural year in 2008. It is very important for us to keep this event free and open to everyone. And I would like to thank our donors and sponsors, including our many departments and institutes across campus, for making today possible. Now, in short time, I want to share a simple but important message with everyone, both in person and for those of you who are online. The research that we do at UCLA and at universities across the country is not just ours. It belongs to each and every one of us, each and every one of you. You are not just the beneficiaries of innovation and entrepreneurship, but you are also a stakeholder. The federal support we rely on represents the shared investment of every American citizen in our collective future. Through your experience at EYU today, I hope you can come to appreciate this perspective more deeply. With that said, it is now my pleasure to welcome and thank our special guest, Professor Terence Tao. Terry needs no introduction. He has made remarkable achievements in science and mathematics. Shortly after receiving his PhD in mathematics at Princeton, Terry came to UCLA in 1999. He has received a number of awards, including the Salem Prize in the year 2000, the Fields Medal in 2016, which is considered the Nobel Prize in mathematics. It's actually harder to get the Fields Medal than the Nobel Prize. The MacArthur Fellowship in 2007, the Crafoord Prize in 2012, and the Breakthrough Prize in Mathematics in 2015. And recently, Terry has been one of our greatest scientific champions on the world stage, lending his voice to the importance of scientific research for society. For all these reasons, the EYU student organizers unanimously voted Terry as the recipient for this year's award. Terry, it is my honor to award you today with the 2025 Science and Pioneer Award. Terry. Now we will hear remarks from Terry.
Well, thank you so much. So I've been here almost 30 years here at UCLA, and I love it. And it's such an honor to be recognized actually for outreach, which is just as important, if not more so, than the research we do here. Although I do also love research. Sorry, is okay. Hope this is better. Right. So so mathematics and science, I mean, I've always loved it, and it's really part. I mean, they work together, and as Miguel said, it is a public resource, and the work we do as one scientist, one mathematician, other scientists build upon, and together we can accomplish great things. So I thought, given that the title of this event is Exploring Universe, I thought maybe the best way to illustrate this is to tell a very old story. So not new research, but work that's been going on for centuries to measure our universe using mathematics and astronomy. So I always liked astronomy as a kid. My parents bought me a little telescope. I would look at constellations. I devoured any book I could find from the library on stars and planets and science fiction. I was very influenced by this old American TV show, Cosmos. Maybe you've heard of it, by Carl Sagan. There's also a remake, which is also pretty good. But then I ended up doing mathematics for my whole career, really. But then after I graduated, I came back and I looked at some of the stuff I loved doing in astronomy, and I found that all the astronomical facts that I had learned, there was a lot of math that made it happen. And it was really pleasing to see how it all connected together. And I could see how math and physics and science and astronomy all became one whole. And so it was actually my first public lecture was on how mathematics explored your universe. I gave this lecture for many years. And then eventually Grant Sanderson, who runs the YouTube channel 3 Blue 1 Brown, contacted me. He liked my presentation. We agreed to turn this into one of his YouTube videos. And he did an amazing job with it. And he's much better at computer graphics than I am. And his presentation is amazing. I urge you to check it out after this talk. So I'll give you a sort of more low-tech version of a part of what we ended up doing, just as a taste. But I think it showcases how all the sciences work together. So I'll be talking about measuring the universe. So is that the right one? All right. Yeah. So, you can look at the sky and you can see the moon and the sun and the stars and the planets. And, it's very natural, even as young children, to ask basic questions like, how far away is the moon? Or how far is it to the sun? Or how far is it to Mars or to Alpha Centauri or whatever? So these are basic questions you can ask just by looking at the sky. And of course, nowadays, they're easy to answer. You just ask ChatGPT, and it will tell you all your answers. Or there's many fine booths here with people who can actually give you more professional answers. But how did we come up, so you can find out that, the distance to the moon is whatever, like 180 million miles or something. But that's not quite right. It's less than that. But yeah, but how can you find out? Because there's no way that you can just take a ruler or something and work these out. There's no possible way to measure these distances directly. But what astronomers have found out over the centuries is they have found many, many clever ways to measure distances indirectly, usually in terms of reference to another distance. So maybe there is a distant galaxy over here, and you want to know how far away it is, and it's way too far to measure in any direct measurement. And there's another galaxy which is a bit closer, but you still can't measure its distance. So neither of these two distances can be worked out. But it turns out, in this case, using something called Hubble's law, you can actually work out the ratio between these two distances. And so you can work out this distance as a multiple of a previous distance. So if an object is really, really far away, you can measure it in terms of one that's a bit closer, and then you measure that in one that's a bit closer still, and you do this about 6 or 7 times until you can get down to something you can actually measure. So it's enormously complicated, and it took centuries to actually work all this out, but we did it. And so this is what we call the cosmic distance ladder. So this is an astronomy textbook, and there's many, many methods stacked on top of each other, starting from the planet Earth all the way to the edge of the universe that we now use to measure distances. So if you take Astronomy 101, or whatever the intro to astronomy class is here at UCLA, you will learn many of these methods. I won't talk about the modern methods. The YouTube video goes into that in more detail. But I'll talk about some of the earliest measurements that we did. Before we had all the telescopes and fancy technology, and all we had was math. So, if you ask ChatGPT, as I said, you will get, or Wikipedia or any other reference, you get all kinds of information about what the Earth is. The Earth is basically a sphere. It's about 6,000 kilometers in diameter, or 4,000 miles. A little bit bulged at the equator. It's not completely spherical, but pretty close to being round. And of course, we can travel into space and have satellites and actually photograph the Earth and see its roundness. But imagine you go back in time, 2,000 years, and so you have no space flight. You can't cross large oceans. You don't even have telescopes or sextants. You basically all you have is math. Can you still actually work out the size of the Earth? Actually, even more basic question: can you even tell the Earth is round? And the amazing thing is that even in like the 3rd century BC, we could do this. The ancient Greeks, basically, they had just developed Euclidean geometry, and they were able to use just geometric facts to work out the size of the Earth. But every time you do this, you have to do something indirect. You always have to use some other object in space as your reference point. So Aristotle was the first to give a scientific argument that the Earth was round in 300 odd BC, and by looking at the moon, because see, we're stuck on the Earth, and so like we can't see. We can only see a tiny little portion of the Earth at once. So there's no way that we can see the Earth as round. Actually, if you're on a really tall mountain, you can kind of start seeing a little bit. But from where we're standing, it's really, really high. But the moon is a much better vantage point. But we can't, in those times, you couldn't go to the moon, but you can still use the moon. So Aristotle argued using lunar eclipses. So lunar eclipses happen every few years or so. There was one in LA just a few months ago. So the Earth casts a shadow because the sun's on one side of the Earth and it casts some sort of shadow. And every so often, the moon falls into the shadow. And that's called a lunar eclipse. So you can get partial lunar eclipses when only part of the moon falls in the shadow. You can get a total lunar eclipse when it's completely in the shadow. But when you have a partial lunar eclipse, you can actually see a little piece of the Earth as a shadow falling on the moon. And so effectively, you can see a little piece of the Earth from the moon's perspective. And what you find is that the shadow of the Earth, no matter how far in the moon goes into the Earth shadow, it's always a circular arc. So if you start pasting lots and lots of these shadows together, you see that the shadow of the Earth in any direction. So lunar eclipses happen in all across the sky, but in any direction, the shadow is always a circle. So whatever shape the Earth is, every single shadow of it is a circular arc. And there's a little mathematical theorem that the only object where all the shadows are circles is a perfect sphere. For example, if the Earth was a disk, like maybe on the top of 4 elephants or something, then if you take a shadow of a round disk on an angle, you don't get a circle, you actually get an ellipse. But it's only the sphere. The sphere is the only shape that has circular shadows in all directions. And so Aristotle, without any technology, was able to argue that the Earth was round. Completely correct argument. Okay, so I said all that. And then only about 100 years afterwards, another Greek scholar, Eratosthenes, who was actually the librarian at Alexandria before it all burned down, actually computed the radius of the Earth. He found a way to actually measure how large the Earth was. He knew it was round from Aristotle, and he measured it in the units of the time, which is a stadium, which is the length of a Greek stadium. And so he measured the radius of the Earth about 40,000 stadia, which in modern units is about 68,000 kilometers. It's about 8%, within 8% of the modern value. It's really, really good accuracy, again, given that they have almost no technology at the time. So this is a story that some of you may know. Now, again, every time you want to measure something in the distance ladder, you need to indirectly measure it using some other object. So you need to look at some other object. So you look at the sun. Actually, don't look directly at the sun. That's not a good idea. But you still use the sun as a reference. So the way the story goes, we only actually have second-hand accounts. We don't have a direct account from Eratosthenes. But apparently, Eratosthenes knew about a town on the Nile in Egypt called Syene. I think nowadays it's called Aswan. But it had a funny property that this town, out of all the towns in Egypt, if you wait until the summer solstice, the longest day of the year, and you go to noon, where the sun is as high as possible. This is the one town in Egypt where on the summer solstice, the sun is actually directly overhead. And there was a well in Syene where if you look down the well and you would see the sun reflected in the water way down below. And it was one day of the year, and only in this town this happened. So Eratosthenes read about this, but Eratosthenes didn't live in Syene. As I said, he was the librarian of Alexandria. So by the way, nowadays the reason why we know this is true is because Syene happens to lie on a certain latitude called the Tropic of Cancer, which is basically the one latitude where this happens. Well, there's also the Tropic of Capricorn, but they didn't know about that one yet. So Eratosthenes was the librarian of Alexandria, but Alexandria doesn't live on the Tropic of Cancer. And so he waited until the summer solstice, and it's not sure whether he actually checked out a well in his own town or he looked at shadows. But in any case, he found that at noon in Alexandria, the sun was not overhead, not directly overhead. That even very tall obelisks and things still cast shadows, whereas in Syene they didn't. So yeah, if you're an ordinary person at this point, you just say, oh, therefore this Syene story was fake news or whatever. Okay, but Eratosthenes had a scientist's mind, and he knew that the Earth was round, and so he figured out what was going on. Is that because the Earth was round, where he was at Alexandria was a little bit curved. His idea of what direction up was just a little bit at an angle of the direction where up was in Syene. So at the same time that the sun was overhead in Syene, was not quite overhead in Alexandria. And in fact, he actually managed to measure. He had a little measuring stick called a gnomon, which is kind of like a portable sundial. And he actually could measure that in Alexandria, the sun was off from the vertical by 7 degrees. And because he knew geometry, he knew therefore that what that meant was that his location in Alexandria and the location in Syene, the angle they made with respect to the center of the Earth was 7 degrees. He also knew the distance between the two towns. So 5,000 stadia, about I think about 600 miles. Or so. I used to think that he actually paid somebody to actually just walk this distance. But apparently at the time there were professional surveyors. They had little primitive machines that would just drop down little stones. And people actually, the military actually wanted to know exactly how long it would take to get from one city to another. So there was actually enough technology at the time to measure this one distance. And so they knew that this distance was 5,000 miles and this angle was 7 degrees. And that's enough data to do a bit of math, and you can actually work out the radius of the Earth that way. So that was what Eratosthenes did. Nowadays, there's something called the Eratosthenes Project. There are actually, people do it not on the solstice, but on the equinoxes. There's a similar thing that works on the equinoxes. And you can get schools from all over the world make little measurements of shadows, and you put them together, and they can, every year, they can reconstruct Eratosthenes calculations. So that's the Earth. Now let's talk about the Moon. Okay, so what shape is the Moon? So this is not a stupid question, because obviously, so we can see the Moon and it looks round, but we always see the same face of the Moon. The Moon always shows only one side. So maybe the Moon is flat, and it's just somehow we're only seeing one flat side. Okay, why is it actually spherical? And how big is it, and how far away is it? So the Greeks could also answer these questions. So Aristotle, again, he explained why we know that the Moon is actually a sphere. Again, because of shadows, and this time because of phases of the Moon. So the Moon has various phases, crescent moon, half moon, gibbous, and so forth. And that's because the sun lights up half of the Moon at any given time. Half the Moon is lit, half the Moon is not lit, and we see half of the Moon, and we don't see the other half of the Moon. But as the position of the Moon changes, the part of the Moon that is lit up by the sun is different from the part of the Moon that we see. And that's why we only see a fraction of the Moon at a time, and that's where phases come from. And it's because that the Moon is round that the portion that is lit up by the sun is always a hemisphere. And so the arc that we see of lit versus not lit, it's called the terminator. It's always an ellipse, actually. So when you look at a hemisphere at an angle, you see an ellipse. If the Moon was flat, you wouldn't get phases. Either the sun would light up the Moon or not light up the Moon. So it would just be on or off. You would not get phases. So you could already tell that the Moon is round. And around the same time, Aristarchus actually worked out the distance to the Moon, not directly in terms of stadia or anything, but in terms of how big the Earth was. He worked out that the distance to the Moon was about 60 times the radius of the Earth. Which is actually almost exactly correct. The distance actually varies a little bit between plus or minus 3, but it is basically 60 Earth radii. And Eratosthenes actually came a little bit after Aristarchus, worked out the radius of the Earth, and so now we know the distance to the Moon. He also worked out the size of the Moon. The Moon is about a third the size of the Earth. So again, you have to use another object. So again, you use the sun, and in particular, the shadows that the sun casts. So the way Aristarchus argued was that he again used lunar eclipses. He knew that the Earth casts a shadow, and the moon passes through the Earth's shadow every so often, and that's what causes lunar eclipses. Now, how big is this shadow? Well, it comes from the Earth, and the Earth is 2 Earth radii wide, and so the Earth's shadow is also about 2 Earth radii wide. It's not quite that there are some asterisks, but roughly speaking, the shadow is basically 2 Earth radii wide. And the moon, if you can actually watch eclipses, and some are short and some are long, but no lunar eclipse takes longer than 3 hours. Okay? The longest lunar eclipse you ever see is 3 hours. And so basically the time taken for the moon to pass through the entirety of Earth's shadow is basically 3 hours. Sometimes they only eclipse Earth's shadow at on the side, and then it takes less than 3 hours. But the full shadow requires 3 hours to pass through. On the other hand, the Greeks knew how long it took the moon to go around the Earth. It's a month, strangely enough, a lunar month, about 28 days. And so the moon traverses this little circle every 28 days, and the circumference here is determined by the distance to the moon. And it takes 3 hours to cross 2 Earth radii. And again, this is just a little bit of math, which they were able to do at the time. And that's how they could work out that the distance to the moon is about 60 Earth radii. So again, no telescopes, not even calculators, or certainly not ChatGPT, but you could work all this stuff out. Now, how about the size of the moon? That was actually also a very similar argument. All you got to do is just watch the moon set. Okay, so the sun rises and sets, and the moon rises and sets, and you can time how long does it take for the moon to set, a full moon, and you'll find that it takes about 2 minutes. So what that means is that as the moon goes around the Earth, actually it's really the Earth spinning that's causing this. But basically, if you look at how the moon appears to go around the Earth, it takes about 2 minutes for the moon to move about 2 moon radii. That's how much it takes for so it takes 2 minutes to travel to 2 moon radii. But how long does it take for the moon to make a full rotation around the Earth? Well, that's a day. Okay, because of the Earth's rotation. Okay, at the time they didn't know whether the Earth was spinning or whether the moon was, or the universe was spinning around the Earth. But it doesn't matter. Either way, it takes 24 hours for the moon's location, as seen from us, to go back to where you start. So it takes 24 hours to traverse an entire moon orbit, and 2 minutes to traverse 2 moon radii. And then you again just do a little bit of math, and you will find you can compute the radius of the moon. It turns out to be 1/3 the radius of the Earth. So as I said, they had no technology. Just to show you just how little, I said all they had was math, but they actually didn't even have all of math. So for example, Aristarchus did not know what pi was. Pi is also known as Archimedes' constant. It was invented by Archimedes a couple decades after Aristarchus. So he didn't even have pi, but he had similar triangles and things. He was still able to work this out without even knowing what pi was, which I find particularly impressive. Okay, so let me close up a little bit. Okay, I'll speed up the sun. So you can also ask the same question about the sun. How far away is the sun, and how large is the sun? And again, the Greeks could do this as well. Although it gets harder and harder the further away you go. And this is about whether they stopped being able to answer these questions, because at some point you actually really do need technology. But they're still able to work out the distance to the sun. And again, you need some other reference object, and there's almost only one choice available, which is the moon. So how do you use the moon to measure the distance to the sun? So one way is to use solar eclipses. Okay, so sometimes the moon passes directly between the Earth and the sun, and you get these beautiful solar eclipses where the sun creates, I guess, this little corona, and the moon blots out the sun almost completely. So there's this amazing coincidence that the moon has actually the same size as viewed from Earth as the sun. So up to within 1%. So if you in a solar eclipse, the moon is not too big or too small. It's just exactly the same size. Which means that if you already know the size and distance of the moon, you can use similar triangles, just a bit more math, and you can work out at least the ratio between the size of the Earth, size of the Sun, and the distance to the Sun. You can't work out how far it is yet, but you can at least work out the ratio because of this similar triangles. So if you can work out the distance to the Sun, you can also work out the size of the Sun, or vice versa. But you still need to work out the distance to the Sun. So, okay, again, you have to use the Moon. Again, that's your only choice, pretty much. And so he again used phases of the Moon, but in a different way. So the Moon has different phases depending on where it is with respect to the Sun. So if the Moon is down here, between the Earth and the Sun, you get a new Moon because the side of the Moon that's lit is the opposite of the side of the Moon that you see. So that you have a new Moon here, so you don't see any of the Moon. If the Moon is on the other side, you get a full Moon because now the side that is lit by the Earth, by the Sun, is the same as the side that you see. And then sometimes you get a half Moon, which is either called a first quarter Moon or a third quarter Moon, where you only see half of the Moon lit and half of the Moon not lit. So half moons, you might think, happen halfway between new moons and full moons. That's what you would think. But if you actually do the geometry carefully, the reason why when you get a half moon when the moon has when the angle between the moon and the Earth and the moon and the Sun is a right angle. When you have a right angle here, then you see exactly 1/2 of the moon being lit up by the Sun. So you get a right angle here, not here. So if this angle is a right angle, then this angle is actually a little bit less than a right angle. So what that means is that half moons actually occur slightly closer to new moons as they do to full moons. So if you can time when a half moon occurs and you can measure exactly what this angle is, you can do a bit of trigonometry. Actually, they didn't have trigonometry. The Indians invented that a few centuries after. You can use similar triangles and things. They had enough math that you could still work out the distance to the Sun with this technique. So Aristotle tried this, and he thought that using the best timing and clocks that he had, he thought that half moons appeared about 6 hours before the midpoint between new moons and half moons. So he thought there was the angle here, the deviation represented 6 hours of movement. And based on that, he thought that the Sun was about 20 times further away than the moon. Now, here's where he lacked technology, because you have to measure this with a really good clock. And the best clocks they had at the time were sundials. And sundials did not work in the dark. They had water clocks, but they're not super accurate. Also, they didn't have telescopes, so it was hard to see exactly when the moon exactly hit halfway. If you do it now with modern telescopes and things, actually the delay is not 6 hours, it's half an hour. So Aristarchus was off by quite a bit. And actually, the Sun is not 20 times further away. It's actually 390 times further away. So he made a big error in his measurements because he didn't have the technology that we have today. But still, he was the first to make a really, really important conclusion. So if you put all this together, he calculated that the Sun was about 7 times bigger than the Earth. Now, he was wrong. The Sun is actually 100 times bigger than the Earth. But he was the first to realize that this little yellow thing in the sky is actually much, much bigger than everything else on the planet put together, times 100, or times 7 for him. And so he was actually the first to realize that since the Sun was that big, so the prevailing theory at the time was that the Sun went around the Earth, and that is ridiculous if the Sun is that big. So he was the first to propose that actually the Earth should be going around the Sun. So he was the first to propose the heliocentric model. So this is an early example of math and astronomy really sort of advancing science, although his ideas did not get accepted for another 1,000 years, but that's another story. All right. I think I won't go through the planets. It's a great story, but I think, okay, the YouTube video will cover all this. I'm going to skip a really cool story. But okay, I hope you get a taste. Yeah, so over the centuries, we've been building up more and more rungs of the ladder. So we managed to measure distances for planets. We were able to use what's called parallax. We could measure once we had telescopes, you could measure distances to nearby stars. Then we developed spectroscopy. We could actually work out the spectrum of stars, and that turned out to reveal a treasure trove of new information. You could then measure stars all across the galaxy using something called domain sequence fitting. And then you can, and then using that, people study what are called variable stars. And then you could actually measure stars' distances to other galaxies as well. And then finally, in the 20th century, we discovered Hubble's law, which is a way which works all across the universe, and you can explore the entire universe like you're going to do today. And so we can actually now start mapping the entire universe. It's still going. We have still not completely worked out. For example, we still don't quite know exactly how big the universe is. We have some lower bound. It's at least like 18 billion light years or something. But we have not actually seen the edge of the universe, and people are still measuring that. We are using really advanced technology at this point. So we're using space probes. There's gravitational astronomy, some of which is done here at UCLA, where we're using these extremely sensitive detectors to measure gravity waves, and we can hear echoes of the Big Bang, and we're learning a lot about the universe there. So it's a really active subject. I think there are booths here if you want to go explore. We'll tell you about what's going on today. But yeah, this is one of the first stories that I learned about how math helps you understand the universe. Basically makes it a more comprehensible and less scary place. So I hope you enjoy the story. As I said, please do check out the videos by 3 Blue 1 Brown, which will explain all this and more with much better graphics. So thank you.
Thank you very much, Professor Tao. Congratulations again for receiving the Education and Pioneer Award from the students. So will you join me and thank Professor Tao once more for a wonderful presentation? Thank you. And now we can let the science, education, and fun continue. There's many booths to visit outside. There's various tours that you can do. And if you want to stay in this room, in a few minutes, we will start a session that deals with standing up for science. So that will happen in probably about roughly 10 minutes or so.